We're going to start this second half of the video by doing the homework problem that was in class. So you recall that we had 0.0001 milliliters of a gas produced of, I think it was Rn 222. And I changed that to 1 times 10 to the minus 7 liters, so I could divide that by 22.4 liters per mole at STP. And that gives you 4.461 times 10 to the minus 9 moles. And this comes from radon 226. If you multiply that number of moles, 4.461 times 10 to the minus 9 moles, times this many grams per mole, you get 1 times 1.01 times 10 to the minus 6 grams. And if you subtract that from the original 1 gram of radon, you end up with 0.9999989 grams of radon. So N0 is 1 gram, and NT is this number right here. And we know that minus the decay constant times time is equal to the natural log of 0.999989 over 1. That's NT over N0. And it's equal to minus natural log. And so, no, just natural log, I'm sorry. And if we put, that means the decay constant is going to be this natural log, which ends up being 1.1 times 10 to the minus 6 divided by 24, and that gives us a decay constant of 4.583 times 10 to the minus 8 hours to the minus 1. So T1 half, which is what was asked, is 0.693 divided by the decay constant times 10 to the minus 8, and that gives us 1.51 times 10 to the minus 7 hours, or 1,725 years. So this is the answer, and we needed to look at the problem, the decay constant equations, before we could actually do this problem. Now let's move on and continue to talk about nuclear fission and nuclear reactors. This is a picture of a nuclear reactor, and you can put inside these nuclear reactors fissionable material and allow for a chain reaction to initiate, and this can be controlled within a situation like this and prevent an explosion. The walls of this are made of steel and concrete, and what you want to do is to produce steam using the heat from the reaction to produce steam, which runs a turbine here and produces, through a generator, produces electricity. The fuel is the fissionable isotope, usually, well, not usually, but such as uranium-235, and you have to have a certain critical mass in order for this to continue on as a self-sustaining reaction. The moderator is a substance that's added to slow the neutrons so that the reaction can be slowed and the reaction can be controlled. Now this is another reactor, and what you want to do is use these rods to cool the reactor. These rods are basically introduced, and the rods of fuel are interspersed within rods of a coolant to keep everything under control. And as I said before, the heat from these reactions are basically used to produce steam, which drives a turbine and produces electricity. The control rods are rods that are put in the fuel, and you adjust this in order to control the rate of reaction. And if you want to increase the rate of reaction, you actually pull the control rods out. And you want to decrease the rate of reaction, you put the control rods back in. So the nuclear reactor core, A, shows the fuel and the control rod assembly, and B is just a cross-sectional area of how that's put together. In 2010, 3 Mile Island broke down and the reactor became damaged. And what ended up happening was that the area was contaminated. Now, this actually occurred during President Carter's administration. This picture was taken in 2010. After the accident, there was a large area of contamination which had to be removed, and a large group of individuals had to be evacuated in order to prevent nuclear or radioactive sickness that is caused by the fallout from radioactive waste. Now, the other kind of reaction, we've been talking all along here about fission, or the splitting of a large nuclei into smaller parts. The other kind of reaction is fusion, nuclear fusion, in which small molecules are pushed together and form a larger molecule. So fusion is the process of converting a light nuclei into a heavier nuclei, which is accompanied by the conversion of the mass into a large amount of energy. When you do this pushing together, the mass deficit occurs, and that is then converted into energy. A fusion reactor is simply a nuclear reactor in which fusion reactions are used to produce the energy. And this is just one example of a fusion reaction. You take two different forms of heavy hydrogen. One's called deuterium, the other's called tritium. Deuterium is 2-1 and tritium is 3-1. These are put together to form an alpha particle and two neutrons. And in the process, significant energy is produced. Now, in medicine, we use radioactive isotopes a great deal to do various types of tests. And a radioactive tracer is essentially an isotope that has the same chemical properties as a stable isotope of the same element. So, for example, you have a radioactive isotope of, say, iodine. It will act chemically in the body like natural iodine and be taken up by the thyroid, which is where most iodine is absorbed. Potassium is the same, and so forth. And so you can tag these, and then you can use them as indicators or to take pictures of various organs in the body. So in this case, this patient received thallium-201, which is taken up by the heart, and then the person is stressed. They are put on a treadmill, and what you want to show is whether or not the thallium makes it to all parts of the heart, and if there's a part of the heart that doesn't have thallium uptake, then that part of the heart is not receiving adequate blood flow, and it's an indication of coronary artery disease. The isotope also can be used as therapy, and so the most common way to do this is with iodine-131, where the initial tracer is used to image the neck, and then you use a higher dose, and it's taken up in the same area, and it treats the, say, thyroid cancer with radiation treatment. So first, a technetium-99 is used, and it can show areas in the body. This on the left here is a generator that's used to separate this technetium from molybdenum. And then the technetium is then injected and goes into the neck. In this case, it's used to treat Graves' disease, which is another thyroid illness. Technetium is used as a tracer that stays in the blood. It's not the same as the iodine. This is a cartoon that shows the radiation treatment with cobalt-60. Now, I'll tell you that cobalt-60 hasn't been used for radiation treatment for a long time. But diagram A shows the patient inside the cobalt holder. The cobalt holder is inside the covered area. You can see that the cobalt is actually a series of sources that surround the patient's head and are all directed in such a way as to focus the radiation at one point. And cobalt is used in this situation because it produces gamma rays. Gamma rays will penetrate very easily and are very high energy and can cause damage in certain areas. At UK, we used to use something called the gamma knife, which was used a different kind of gamma source, and you could direct it and treat tumors that were 2 or 3 centimeters in size inside the brain without treating the surrounding brain. And it was a knife. It was almost like taking a knife in and cutting out the abnormal tissue and leaving the normal tissue intact. So cobalt, as I said, undergoes significant decays, and during these decays, gamma radiation is emitted, and you end up with nickel 60. Radiation can also be used to examine luggage. X-rays are used to examine luggage, and it can be used to destroy contamination that can cause fruit to spoil. UV radiation is used to kill bacteria, and X-rays are used in this picture on the left to look inside luggage. X-rays, as you know, are also used to image bones. UV radiation, in addition to being a good disinfectant, is also what's inside a tanning bed, things of that nature. Smoke detectors actually also have a radioactive source. It's a very small radioactive source, AM Americum 241. It emits these particles that ionize the air and in the process create an electrical current. And if a smoke occurs, this impedes this flow of ions, and the interruption of the current causes the alarm to go off. Radiation works by damaging DNA inside of cells, and because cancer cells are preferentially multiplying, they are more sensitive to DNA damage. Regrettably, if you take normal cells, though, and damage their DNA, you can actually produce cancer or cause cancer to occur by the process of mutation. This diagram shows that process where radiation is causing damage, which ends up causing a tumor to occur. There are two kinds of radiation: non-ionizing radiation, which are radiation that does not interact with biological molecules. In general, that's like UV radiation, well, like light and microwaves. And then ionizing radiation, which does interact with biological molecules and causes electrons to be knocked out of those molecules. UV, X-rays, gamma rays, alpha particles, beta particles, etc. are all forms of ionizing radiation. So radiation causes harm to biological systems by damaging the DNA. And this damage, if it's not repaired, ends up causing cancer. And the lower frequency, lower energy microwaves, infrared, visible light, all on the left on this slide, do not ionize and do not have the damaging interactions that the higher energy ultraviolet, X-ray, gamma rays. You have increasing frequency, you have increasing energy, and increasing interactions with the biological molecules. So ionizing radiation can directly damage molecules, or it can cause changes in water, causing those changed water molecules to interact with biological molecules and indirectly damaging the biological molecules. Actually, another very important molecule that can be damaged is something called superoxide, which is oxygen. You have oxygen, which is regular, -2. Then you have peroxide, which is oxygen 2, and it has a -1 charge. Superoxide is oxygen 2 with a -2 charge, and it is very reactive and damages biological molecules. And it's one of the things that is thought to cause aging. The ability for different types of radiation to pass through materials is shown, and the least penetrating, as you can see, is alpha, and the greatest penetration is gamma radiation. Houses are always checked for radon. Radon seeps into houses and other buildings from the rocks, and radon that enters into the houses can, if the concentration becomes a certain height, there's an increased risk of lung cancer from breathing in these radon particles. Now, the measurement of radioactive decay is in something called a becquerel, and a becquerel is 1 disintegration per second. A curie is a much larger unit, and it's what we usually use in medicine. It's 3.7 times 10 to the 10th becquerels. So radiation absorbed dose, or RAD, is equal to 0.01 joules per kilogram of tissue. So when you hear people talking about so many rads of radiation, this is what they're talking about, the amount of energy absorbed from the radiation. Devices shown in the picture here are used to measure the exposure of radiation. X-ray workers, people who work around X-rays, will have little badges like shown on the right here. And inside those badges is film. And it's set up in such a way as to measure the amount of radiation. If it changes, then this person has been exposed to a certain level of radiation. And this radiation is measured in various ways. One is called a sievert, which is the tissue damage caused by radiation. And a Röntgen equivalent for man is the unit of radiation damage that is used most commonly in radiation. You've heard of rems. 1 rem is equal to 1 sievert. And relative biological effectiveness is an approximate measure of the relative damage done by the radiation. So different units are used to measure the rate of emission of radioactive sources, and the energy that's absorbed from the source, and the amount of tissue damage that is done by the radiation that's absorbed. Your total annual radiation exposure per person in the United States is about 620 millirems, so thousandths of a rem, not a complete rem. Here, this diagram shows various sources and their relative amounts of radiation, and you can see that a whole body CAT scan is 1,000 millirems. So it's more than if you get 1 CAT scan, it's almost twice as much as the average annual exposure.